Thank you for the introduction. Yep. So thank you everyone for being here. My name is Meng. I'll be presenting our paper on accelerating quantum circuits simulation under noise via computational reuse. So as our title suggests, we are focusing on this noisy simulation of quantum circuits. So why do we care about it? So to answer this, let's first look at the quantum papers this year from ISCA'25. This year we have 16 papers spread across 3 quantum sessions. This represents a fairly large sample size, given that it's only just one venue for the quantum computing research. Out of those papers, 87 of them rely on simulators, with most of them using the noisy simulations. On the other hand, only 27% use actual quantum devices to verify or demonstrate their designs. So why does the quantum computing research community rely so heavily on those simulators? Well, first and foremost, we have a very limited access to the hardware. So right now, there's only about 20 devices that are publicly available, with most of them coming from the IBM. In fact, IBM hosts roughly 12 devices that are open access. As a result, the queues for accessing those devices are often very long. Users sometimes have to wait hours or even days just to get access to run their experiments. Of course, there are some private groups that have their own devices building for their own testing, but those are not publicly accessible, so we're not considering them here. Another reason is the simulator gives us the ability to configure device parameters like the error rates. We know that the current quantum devices are still quite noisy and not capable of running large-scale quantum circuits. However, in some research, we are focusing on large-scale quantum algorithm designs. And to verify those quantum circuit designs, we would need to run large-scale quantum circuit simulations. And we can run those simulations under different scenarios like error rates, topologies, essentially a range of device parameters. And in simulations, those can easily be changed with demand. But noise simulation is crucial in our research community, but it's also very costly. So let's first look at the memory overhead in the noise simulations. The standard approach to do the simulating noise is using the so-called density matrix simulator. The problem with this method is that its memory's usage scale as 4 to the power of n, with an n being the number of qubits. So even on the world's largest HPC currently available, we can only simulate maybe around 24 qubits. A workaround to the density matrix simulator is using the state vector simulator, which despite also scale as exponentially, but now is 2 to the power of number of qubits. So now it gives us the ability to simulate some medium to large scale quantum circuits, maybe in the range of 30 plus qubits. So the state vector simulator is what we're focusing in our paper. But it also has a main limitation, which is the runtime overhead. To understand this overhead, let's first look at how the quantum circuit simulation works. Here's the quantum circuit we want to simulate. It contains a list of gates. Here we're showing 4 gates, A, B, C, and D. We start with an initial state. This state is usually some trivial state, like the all-0 state. We then apply each gate to this state, getting some intermediate states, and apply the next gate all the way to the final one. And here we got our final state vectors. And this is the results we're getting. And this is how the noise-free simulation works. To model the effect of noise, we first need to introduce some noisy operators that model the effect of noise. So for example, with a depolarizing noise channel, which is one of the most commonly used noise channels, the noise operators are the Pauli X, Y, and Z gates. Now, instead of just applying the individual gates, after each gate, we will need to add one of these noise operators to model the effect of noise. The probability of adding those operators is given by the gate fidelity or the error rates. So for example, if your gate fidelity is 99%, then in the 99% of the time, we won't add any noise operators. But in the 1% of the time, we're gonna add some noise operators to model the noise. So as a result, our original quantum circuit now becomes a noisy version. So in this case, in this example, we have some errors that are added after the gate A and C, while we leave the gate B and D unaffected. So of course, this is just one way to insert noise. There are many possible configurations for where the noise operators can be added. So to run a full simulation, we need to repeat this process for multiple shots. And for each individual shots, we need to sample a different version, a different noise version. So this process is known as the Monte Carlo simulation, and it has a huge runtime overhead. For example, consider this a 20-qubit quantum Fourier transform circuit. When we're running the ideal simulation, it only takes about roughly 90 milliseconds to finish. It's pretty quick. But if considering we're running a noisy simulation with 32,000 shots, the runtime jumps all the way to 46 minutes. It's a huge increase, despite it's only using 16 megabytes of memory for each state vector. So seeing this, you may wonder that, well, since each state vector only takes about 16 megabytes of memory, on the current devices, classical platforms, we usually have gigabytes or even terabytes of memory. Why not would we just run multiple shots in parallel? And those Monte Carlo simulations are embarrassingly parallel, so they are easily to be parallelizable. Well, it won't work here because even though each state vector is pretty small, it already consumes most of the computational resources available on your CPU or GPU cores. For example, when running the same simulation, now with parallel shots, starting with 1, 2, and all the way to 16 parallel shots, we see the most speed up with around 8 parallel shots at around 2.5 times speed up. This is way lower than the expected 8 times speed up of the running 8 parallel shots. What makes the problem worse is that if we increase the number of parallel shots after that, then we're getting a negative result. So just naively increase the number of parallel shots won't solve this runtime issue. So we aim to address this runtime issue by fundamentally reducing the total computation required for noisy simulations. The key observation here is that there are computational redundancies in those noisy versions of the circuits. So for example, let's look at those dashed portions of the circuits. In shot 1 and 2, we see an overlap where the gates, including the noise operators, are all identical. And similarly, in shots 3 and 4, they are almost the same, but differing only by one noise operator. So this allows us to run the first part of the circuit, cache the results, and then reuse them for the later half of the circuits, both across shot 1 and 2 and across shot 3 and 4. This approach gives us a 25% reduction in computation. So given this observation, we proposed TQSIM, a tree-based quantum circuit simulator, to leverage this redundancy to speed up the simulation. So the first step in TQSIM is to partition the circuit into subcircuits. The partition takes multiple factors into account, including the available memories that we have on our system. That will limit how many intermediate states we can cache for reuse at a time. And it also considers the cost of doing the reuse, because each reuse involves making a copy of a state and later reuse that state for another subcircuit. So there's a cost associated with that process. We want to ensure that the cost of doing such cachings do not outweigh the speed up we are aiming to achieve. So once the circuit is partitioned, the next step is determining how to reuse those intermediate states. So let's first look at the baseline simulation flow. We use a simulation tree here to demonstrate the flow of simulation. So in this case, there's no reuse for each individual shot. We simply start from the first subcircuit, then proceed directly to the last one. In the reuse case, we have fewer higher level subcircuits, and their results are reused by multiple lower level subcircuits. So from this, we can see that determining how we reuse the state is almost identical or equivalent to deciding how we want to perform node reduction in our simulation tree. So our baseline simulation tree now becomes the one shown on the right, with many fewer nodes. Recall that each node corresponds to one subcircuit, so the reduction in the node counts is directly proportional to the computational reduction. Of course, we can't reduce as many as we want because that would definitely lead to accuracy issues. We need to ensure that even if we reuse intermediate states, we maintain a high level of accuracy throughout the process. So from the simulation tree on the right, we can clearly see that the first level of the simulation tree has the fewest number of nodes, while the number of nodes increases as we move to the lower level of the simulation trees. The key thing we need to ensure is that the first level contains the minimum number of nodes that can effectively represent the first level nodes in the baseline simulation tree. Essentially, this is the downsampling process where we reduce the original number of nodes to a smaller set. In this process, there are a few key metrics we need to consider. First is the variance in the original set, which can be captured by the error rate in the circuit. This is straightforward because when we have a zero error rate, all the nodes are identical. So you only need one to represent the entire set. However, as the error rate increases, there's a higher chance of errors being inserted at different locations, leading to more variance. With a higher variance, more nodes will be needed to in the downsampled side to represent the full distribution. The second factor is the statistical difference in confidence. Naturally, we want the best accuracy possible, but we can't aim for 100% accuracy, and that would simply bring us back to the original number of nodes. In the statistical analysis, we typically set the confidence interval and the margin of error. For our case, we set the confidence interval to 99% and margin of error to 0.05. And lastly is the total number of nodes in the original baseline simulation tree, or total number of shots. So with these three values, we can then use the formula on the right to calculate the minimum number of samples needed in the downsample node set. This formula is typically used in the statistics to determine the minimum number of samples that is required to fully represent a population. So here we present the result of TQSIM. We first show the speed up result. We evaluated TQSIM across 48 circuit benchmarks, spanning a wide range of qubits and gate counts. As the number of gate increases, we can observe that TQSIM achieves better speed up because it provides more opportunities for circuit partitioning and reuse. And overall, we observe a speed up of up to 3.9 times, and on average of 2.5 times. It's important to note here is that we have tested TQSIM on CPU, GPU, and even on multi-node CPU, GPU platforms. And in all cases, we observe a similar speed-up numbers. This consistent performance is because TQSIM fundamentally reduces the total computation required. So the speed-up we're observing here is agnostic to the underlying physical platform. Here's the accuracy result with 1 bar for each circuit class. And there are 8 benchmark circuits in each class. Note that we're comparing the difference in the normalized fidelity, not the absolute fidelity. In the noisy simulations, our goal is to get the fidelity result as close to the baseline as possible, rather than improving the fidelity. So in terms of the difference, we observe an average difference of just 0.007, with a maximum difference for individual circuits being 0.016. This is a very small difference. And this is using the depolarizing noise channel. We further tested on other noise channels, including thermal relaxation, amplitude damping, and physical phase dampings. And across all the noise models, we observe a very small accuracy loss with TQSIM. So to conclude, noise simulations play a crucial role in quantum research, but its runtime grows much faster than its memory overhead. TQSIM leverages computational reuse in the noise simulations, and it achieves up to 3 times speed up with a minimal fidelity loss. Our code is open source on GitHub, and you can find our paper there as well. So lastly, I want to thank my collaborators and my advisor, and that concludes my talk. I'm happy to take any questions you may have.
Thank you very much.